Billions of years ago, Mars looked nothing like the cold, barren desert we know today. Rivers carved deep channels across its surface. Lakes pooled in ancient craters. A thick atmosphere wrapped around the planet, keeping it warm enough for liquid water to exist. And then, something catastrophic happened. Slowly, relentlessly, Mars began to lose its atmosphere. The water evaporated. The rivers dried up. The lakes vanished. What was once a world that might have harbored life became a frozen wasteland. Scientists have been trying to answer this mystery for decades. Where did the Martian atmosphere go? Why did Earth manage to hold onto its protective blanket of air while our neighboring planet lost almost everything? The answers to these questions aren't just academic curiosities. They could tell us whether life ever existed on Mars. They could help us understand how planets evolve over time. And perhaps most importantly, they could reveal something crucial about Earth's own future. Now, two small spacecraft are being prepared for a journey that could finally unlock these secrets. Their names are Blue and Gold, named after the colors of the University of California, Berkeley, where the mission was conceived. Together, they form ESCAPADE, the Escape and Plasma Acceleration and Dynamics Explorers. This is one of the most ambitious small satellite missions ever attempted, and it's heading to Mars with a very specific goal: to watch, in real time, how the solar wind strips away what remains of the Martian atmosphere. But before we dive into what ESCAPADE will do and why it matters, we need to understand the fundamental problem these twin spacecraft are trying to solve. We need to go back to the beginning, to a time when Mars and Earth were not so different from each other. 4.5 billion years ago, when our solar system was young, both Mars and Earth formed from the same swirling disk of gas and dust that surrounded our newborn Sunday. Both planets started with similar ingredients. Both developed atmospheres. Both had volcanic activity that pumped gases into their skies. For the first few 100 million years, Mars might have been even more hospitable than Earth. Mars is farther from the Sun, which means it receives less solar radiation. But in those early days, when the Sun was actually dimmer than it is today, this distance might have been an advantage. Mars had a thick atmosphere rich in carbon dioxide, which created a greenhouse effect that kept the planet warm. Evidence from orbital observations and surface rovers suggests that liquid water flowed on Mars for hundreds of millions of years, maybe even longer. So what went wrong? The answer lies beneath the surface. Deep inside Earth, our planet's core is still churning with heat. This internal furnace generates something absolutely essential for life: a global magnetic field. Earth's magnetic field extends far out into space, creating a protective bubble called the magnetosphere. This magnetosphere acts like an invisible shield, deflecting the constant stream of charged particles that the sun hurls at us. This stream of particles is called the solar wind. It's not wind in the traditional sense. There's no air in space. Instead, it's a flow of electrons and protons that the sun continuously ejects from its outer atmosphere. The solar wind travels at speeds between 400 and 800 kilometers per second. When it reaches Earth, our magnetic field forces most of these particles to flow around our planet, like water flowing around a rock in a stream. Mars once had a magnetic field too. We know this because certain ancient rocks on Mars are magnetized, preserving a record of the field that existed when they formed. But about 4 billion years ago, something happened inside Mars. The planet's core cooled down. The churning motion that generated the magnetic field stopped. And without that protective shield, Mars was left exposed to the full fury of the solar wind. This is where our story really begins. Without a global magnetic field, Mars became vulnerable. The solar wind began to interact directly with the upper atmosphere of Mars, slowly but surely stripping it away. Molecule by molecule, ion by ion. Over billions of years, this process transformed Mars from a potentially habitable world into the cold desert we see today. But here's the thing, we don't fully understand how this process works. We know it happens. We can see the evidence in the thin, wispy atmosphere that remains on Mars today. Less than 1% of the density of Earth's atmosphere. We've measured particles escaping from Mars using previous missions. But the details remain frustratingly unclear. How exactly does the solar wind interact with the Martian atmosphere? What determines how much atmosphere is lost during calm solar conditions versus during violent solar storms? How did this process change over time as the sun evolved? And could something similar ever happen to Earth? These are the questions that ESCAPADE was designed to answer. The mission emerged from a class of NASA programs designed to do more science with less money. Traditional planetary missions cost hundreds of millions or even billions of dollars. They take decades to plan, build, and execute. But in recent years, NASA has been experimenting with smaller, faster, cheaper approaches. ESCAPADE is part of this new philosophy. The mission is classified as a small, innovative missions for planetary exploration, or SIMPLEX. These missions are capped at relatively modest budgets compared to flagship missions, which forces engineers and scientists to be creative. They can't build massive spacecraft with every instrument imaginable. Instead, they have to focus on specific questions and design targeted solutions. For ESCAPADE, that focus is on understanding the dynamics of atmospheric escape. And to do that, the mission needed something that no previous Mars mission has ever had: the ability to measure the same phenomenon from two different locations simultaneously. Think about it this way. When you're trying to understand a complex, three-dimensional process, like how the solar wind wraps around Mars and drags away atmosphere particles, taking measurements from a single location is like trying to understand a symphony by listening through a keyhole. You can hear something, but you're missing most of the picture. Previous missions to Mars, like NASA's MAVEN spacecraft, have provided invaluable data about atmospheric escape. MAVEN has been orbiting Mars since 2014, measuring the composition and behavior of the upper atmosphere. It has confirmed that the solar wind is indeed stripping away the Martian atmosphere, and has even estimated how much atmosphere Mars has lost over time. But MAVEN is a single spacecraft. It can only be in one place at a time. When it measures something interesting, a burst of escaping ions, for example, it can't tell whether that burst is happening everywhere around Mars or just in the specific location where MAVEN happens to be. It can't distinguish between changes that happen because conditions at Mars are changing versus changes that happen simply because MAVEN moved to a different location. ESCAPADE solves this problem by sending two identical spacecraft to Mars. Blue and Gold will orbit the planet together, but on different trajectories. Sometimes they'll be on opposite sides of Mars. Sometimes they'll be close together. Sometimes one will be in the solar wind while the other is in Mars's magnetotail, the region behind the planet where the solar wind has been deflected. By comparing what blue sees with what gold sees at the same moment, scientists can finally separate spatial variations from temporal variations. They can watch how the solar wind interacts with different parts of the Martian environment simultaneously. They can track how disturbances propagate through the system. They can build a truly three-dimensional picture of the escape process. This is the power of twin spacecraft observations. It's a technique that has been used successfully at Earth, where missions like Themis have deployed multiple satellites to study our own magnetosphere. But it's never been done at another planet before. ESCAPADE will be the first. Let's talk about the spacecraft themselves. Blue and gold are small, really small compared to traditional planetary missions. Each one is about the size of a mini refrigerator when its solar panels are folded up. They weigh only about 120 kilograms each, less than many adult humans. In the world of spacecraft engineering, they're considered CubeSat class, though they're actually a bit larger than standard CubeSats. But don't let their size fool you. These little spacecraft are packed with sophisticated instruments designed specifically for their mission. Each one carries 3 main scientific instruments, and together they can measure everything needed to understand how the solar wind interacts with Mars. The first instrument is called EMAG, which stands for Electrostatic Analyzer and Magnetometer. Actually, let me correct that. EMAG is specifically the magnetometer, while ESA is the electron electrostatic analyzer. These instruments work together to measure the magnetic field and the electrons that flow through the space around Mars. The magnetometer is crucial because it measures the magnetic field. Even though Mars doesn't have a global magnetic field anymore, the solar wind carries its own magnetic field with it. This interplanetary magnetic field gets draped around Mars and creates complex structures in the space near the planet. By measuring how this field changes over time in space, scientists can understand how energy is being transferred from the solar wind to the Martian atmosphere. The electron analyzer measures the electrons in the solar wind and in the Martian environment. Electrons are important because they carry information about what's happening in the plasma, the hot, ionized gas that makes up the solar wind. By measuring the energy and direction of electrons, scientists can identify different regions around Mars, from the undisturbed solar wind to the boundary where it first encounters Mars, to the region where atmospheric particles are being stripped away. The second major instrument is SWIA, the Solar Wind Ion Analyzer. This instrument measures the ions, the positively charged particles in the solar wind. The solar wind is mostly made up of protons, which are hydrogen atoms that have lost their electrons. SWIA can measure how fast these ions are moving, what direction they're going, and how their properties change as they interact with Mars. The third instrument is called EUV, the Extreme Ultraviolet Monitor. This instrument doesn't look at Mars at all. Instead, it looks at the sun. EUV measures the amount of extreme ultraviolet light coming from the sun, which is important because this radiation is what ionizes the Martian atmosphere in the first place. The sun's EUV output varies constantly, especially during solar flares and other solar activity. By measuring these variations, scientists can understand how changes in solar radiation affect atmospheric escape. Together, these 3 instruments give each spacecraft a complete picture of the plasma environment around Mars. And because both blue and gold carry identical instrument suites, scientists can directly compare measurements from different locations without worrying about instrumental differences. The mission design is elegant in its simplicity. Both spacecraft will be launched together and travel to Mars as a pair. Once they arrive, they'll enter orbit around Mars, but their orbits will be carefully designed to give different perspectives on the escape process. The orbits are highly elliptical, meaning the spacecraft will swing close to Mars at their lowest point and far away at their highest point. This is important because the interaction between the solar wind and Mars happens at different distances from the planet. Close in, you can see the atmospheric ions being picked up by the solar wind. Farther out, you can see the larger scale structures of the magnetotail and the bow shock, the boundary where the solar wind first starts to slow down as it approaches Mars. By having two spacecraft on different orbits, ESCAPADE can sample these different regions simultaneously. One spacecraft might be deep in the magnetotail, measuring escaping ions, while the other is at the bow shock, measuring the incoming solar wind. This allows scientists to directly connect cause and effect in ways that have never been possible before. The nominal mission duration is 11 months of science operations, though everyone hopes the spacecraft will last longer. Mars missions have a history of exceeding their expected lifetimes. MAVEN, for example, is still operating a decade after it arrived at Mars. If blue and gold prove similarly robust, they could provide years of valuable data. Now, let's dive deeper into the science. What exactly is happening at Mars that causes atmospheric escape? The process is more complex than you might think, and there are actually several different mechanisms at work. The most important mechanism is called ion pickup or sputtering. Here's how it works. High in a Martian atmosphere, solar ultraviolet radiation strikes molecules of carbon dioxide, nitrogen, and other gases. This radiation is energetic enough to knock electrons off these molecules, turning them into positively charged ions. Once ionized, these particles are no longer electrically neutral. They can feel the electromagnetic fields carried by the solar wind. The solar wind's magnetic field sweeps past Mars at incredible speeds, and when it encounters these newly created ions, it grabs them and accelerates them away from Mars. It's a bit like a cosmic vacuum cleaner, picking up ionized particles and carrying them off into space. This process happens constantly, day and night, and it's been happening for billions of years. But the rate of escape isn't constant. It varies dramatically depending on conditions. When the sun is quiet, the escape rate is relatively low. But when the sun is active, during solar flares, coronal mass ejections, and other violent events, the escape rate can increase by a factor of 10 or more. This is one of the key things ESCAPADE is designed to study. By having two spacecraft, the mission can measure how quickly disturbances from the sun propagate through the Mars system. When a burst of solar wind arrives at Mars, how long does it take for the escape rate to increase? How does the disturbance spread around the planet? How long do the effects last after the disturbance passes? These questions might sound academic, but they have profound implications for understanding Mars's history. The sun was much more active when it was young. Solar flares were more frequent and more powerful. Coronal mass ejections were more common. If escape rates during these events are dramatically higher than during quiet times, then most of Mars's atmospheric loss might have happened during brief but intense periods of solar activity rather than through a steady, gradual process. This matters for understanding whether Mars could have sustained life. If the atmosphere was stripped away quickly, in just a few 100 million years, then there might not have been enough time for life to evolve. But if the process was slower, stretching over 1 billion years or more, then life might have had a chance to get started before conditions became too harsh. There's another mechanism of atmospheric escape that ESCAPADE will study, and it's even more dramatic. During severe solar storms, something called a coronal mass ejection can hit Mars. A coronal mass ejection, or CME, is essentially a massive bubble of magnetized plasma that the sun ejects into space. When a CME hits a planet, the effects can be dramatic. At Earth, CMEs cause geomagnetic storms that can disrupt power grids, damage satellites, and create beautiful auroras. At Mars, without a global magnetic field to provide protection, the effects are even more severe. The CME can temporarily compress the entire Martian plasma environment, pushing the boundary between the solar wind and the atmosphere down to much lower altitudes. This exposes more of the atmosphere to direct erosion. MAVEN has observed several CME impacts at Mars, and the results were striking. The escape rate spiked dramatically during these events, sometimes by factors of 10 or 20. But with only one spacecraft, MAVEN couldn't capture the full three-dimensional picture of what was happening. It couldn't tell whether the escape was happening uniformly around the planet or concentrated in specific regions. It couldn't track how the disturbance evolved over time. ESCAPADE will change that. When a CME hits Mars while both spacecraft are operating, scientists will have unprecedented data on how the event unfolds. They'll be able to track the disturbance as it wraps around Mars, measure the escape from multiple locations simultaneously, and build a complete picture of how these dramatic events affect the Martian atmosphere. There's one more aspect of the Mars environment that makes ESCAPADE's twin spacecraft approach especially valuable: crustal magnetic fields. Even though Mars doesn't have a global magnetic field anymore, it still has localized magnetic fields in certain regions of its crust. These are remnants of the ancient global field, frozen into rocks that formed billions of years ago when the dynamo was still active. These crustal magnetic fields are strongest in the southern hemisphere, in some of the oldest terrain on Mars. They create mini magnetospheres, small regions where the magnetic field is strong enough to deflect the solar wind and protect the atmosphere beneath them. But these regions are patchy and irregular, nothing like Earth's uniform global field. The interaction between the solar wind and these crustal fields is complex and poorly understood. The solar wind doesn't flow smoothly over these regions. Instead, it creates turbulent boundaries where energy can be transferred in complicated ways. Sometimes these crustal fields seem to protect the atmosphere beneath them. Other times, they seem to enhance escape by channeling energy into the atmosphere. With two spacecraft, ESCAPADE can study these crustal field regions in ways that have never been possible. One spacecraft can be over a region with strong crustal fields, while the other is over a region with weak or no crustal fields. By comparing the two, scientists can finally understand how these localized magnetic fields affect atmospheric escape. This is particularly important because some scientists have proposed using artificial magnetic fields to protect future Mars colonists from radiation and perhaps even to help rebuild the Martian atmosphere. If we're going to seriously consider such schemes, we need to understand how magnetic fields interact with the solar wind at Mars. ESCAPADE will provide crucial data for evaluating these ideas. Let's step back for a moment and consider the broader context of this mission. Why does understanding atmospheric escape at Mars matter for us here on Earth? First, there's the question of habitability. Mars today is not a place where life, as we know it, could survive on the surface. The atmosphere is too thin to provide protection from radiation. Liquid water cannot exist because the atmospheric pressure is below the triple point of water. It would immediately boil away. The temperature fluctuates wildly between day and night. But if Mars once had a thicker atmosphere and liquid water, it might once have been habitable. And if life ever arose on Mars, remnants might still exist, frozen in the subsurface ice, or sheltered in caves, or hidden in the soil. Understanding how and when Mars lost its atmosphere helps us understand when and whether life could have existed there. Second, there's the question of Earth's future. Our planet has a strong magnetic field now, but that field has varied in strength over geological time. There have been periods when the field was much weaker than today, and periods when it reversed polarity entirely. During these times, Earth would have been more vulnerable to atmospheric loss. By studying how the solar wind interacts with Mars, a planet without a global field, we can better understand what would happen to Earth if our magnetic field weakened significantly. This isn't just a theoretical concern. Some scientists believe Earth's magnetic field may be in the early stages of a polarity reversal right now, which could take thousands of years to complete. During that transition, the field would be much weaker and more disorganized. What would that mean for our atmosphere? ESCAPADE can help answer that question by providing detailed data on how unmagnetized planets interact with the solar wind. The physics is universal. The same processes that strip Mars's atmosphere would affect Earth's atmosphere if our magnetic field disappeared. Understanding Mars helps us understand our own planet. Third, there's the practical question of future exploration. If humans are ever going to live on Mars, and many people believe that's inevitable, we need to understand the radiation environment. The Martian surface is constantly bombarded by high-energy particles from the solar wind and from cosmic rays. Without a thick atmosphere to absorb these particles, radiation levels on Mars are much higher than on Earth. ESCAPADE will help characterize this radiation environment by measuring the particles in the space around Mars. This data is essential for designing spacecraft, spacesuits, and habitats that can protect future Mars colonists. The mission also represents a new approach to planetary exploration. For decades, NASA's planetary missions have been dominated by large, expensive, one-of-a-kind spacecraft. These missions have been enormously successful. They've given us rovers on Mars, orbiters at every planet, and probes that have visited comets and asteroids. But they're also slow and expensive. It can take 20 years from initial concept to final data for a major planetary mission. ESCAPADE represents a different philosophy. By keeping the spacecraft small and the mission focused, the team was able to move much faster than traditional planetary missions. The scientific payload was designed specifically to answer a set of well-defined questions rather than trying to do a little bit of everything. The result is a mission that costs a fraction of traditional planetary missions, but can still deliver transformative science. If ESCAPADE succeeds, it will demonstrate that this approach works for planetary science. We might see more twin spacecraft missions in the future, perhaps to Venus, or to the moons of Jupiter and Saturn, or to asteroids. The ability to make simultaneous measurements from multiple locations is so powerful that it's worth designing missions around this capability. Now let me tell you about the journey these spacecraft will take to reach Mars. Getting to another planet is never simple, and ESCAPADE's path has been particularly eventful. The mission was originally supposed to launch in 2024 on a commercial rocket. The plan was to hitch a ride as a secondary payload on a larger mission, which is one of the ways small missions keep costs down. But space missions rarely go according to plan. There were delays. There were technical challenges. The launch schedule slipped. Eventually, ESCAPADE was manifested on a launch in late 2024, riding alongside a commercial lunar lander. But even that path wasn't straightforward. The complexities of coordinating multiple payloads on a single rocket, each with different requirements and destinations, created challenges that the team had to work through. Once launched, Blue and Gold will travel together through interplanetary space for several months before arriving at Mars. The transfer orbit is carefully calculated to use as little fuel as possible while still getting the spacecraft to Mars at the right time and with the right velocity to enter orbit. When they arrive at Mars, the spacecraft will perform a critical maneuver, Mars orbit insertion. This is one of the most dangerous moments of any Mars mission. The spacecraft must fire their engines at exactly the right time and for exactly the right duration to slow down enough to be captured by Mars's gravity. Fire too little, and they'll sail right past Mars and be lost in deep space. Fire too much, and they'll enter an orbit that's too low, possibly crashing into the planet or burning up in the atmosphere. For ESCAPADE, this maneuver is especially challenging because both spacecraft must perform it successfully. Losing one spacecraft would severely compromise the mission's ability to do simultaneous two-point measurements. The team has spent years planning and testing to ensure both Blue and Gold can execute this maneuver flawlessly. Once in orbit, the spacecraft will go through a commissioning phase where all systems are checked out and the instruments are calibrated. Then the real science begins. The science phase is designed to capture a range of different conditions at Mars. Over the course of the mission, the spacecraft will observe Mars during quiet solar conditions and during active solar events. They'll see different seasons on Mars as the planet's tilt changes its orientation relative to the Sun. They'll observe the crustal magnetic field regions from different angles and at different times. All of this data will be transmitted back to Earth using the Deep Space Network, NASA's array of giant radio antennas that communicate with spacecraft throughout the solar system. The data rates for small spacecraft are limited, so the team has had to be clever about what data to send home and when. Priority is given to the most scientifically valuable measurements, with lower priority data transmitted when communication time allows. Back on Earth, the science team will be working around the clock to analyze the incoming data. The simultaneous two-point measurements will enable entirely new types of analysis that weren't possible with single spacecraft missions. They'll be able to measure how fast disturbances travel through the Martian plasma environment. They'll be able to separate spatial and temporal variations for the first time. They'll be able to test theoretical models of atmospheric escape in ways that have never been possible before. The team includes scientists from institutions around the world. The principal investigator is based at the University of California, Berkeley, which has a long history of space plasma physics research. But collaborators come from NASA centers, other universities, and international partners. This global team brings diverse expertise and perspectives to the mission. Let's talk about some of the specific scientific questions ESCAPADE will address. These questions have been debated by planetary scientists for decades, and ESCAPADE has the potential to finally provide definitive answers. Question 1. How does the solar wind transfer energy to the Martian atmosphere? This might sound like a simple question, but it's actually quite complex. The solar wind carries energy in several forms: kinetic energy from the motion of particles, thermal energy from the temperature of the plasma, and magnetic energy from the interplanetary magnetic field. All of these can potentially be transferred to the Martian atmosphere, but the relative importance of each is unclear. ESCAPADE will measure all three forms of energy at 2 points simultaneously, allowing scientists to track how energy flows through the system. What packet of solar wind energy arrives at Mars? Where does it go? How much is absorbed by the atmosphere? How much is diverted around the planet? How much ends up accelerating atmospheric particles to escape velocity? Question 2. What determines the structure of the induced magnetosphere? Mars doesn't have a global magnetic field, but it does have an induced magnetosphere, a region where the magnetic field of the solar wind piles up against the planet and creates a pseudomagnetosphere. The structure of this induced magnetosphere determines how well Mars is protected from the solar wind. Previous missions have shown that the induced magnetosphere is highly variable. Its size and shape change depending on solar wind conditions, solar EUV output, and the orientation of the interplanetary magnetic field. But with only single-point measurements, scientists haven't been able to determine what causes this variability. ESCAPADE's 2-point measurements will allow scientists to distinguish between two possibilities. First, the induced magnetosphere might breathe in and out globally, expanding and contracting uniformly in response to changing conditions. Second, the changes might be more localized, with different parts of the induced magnetosphere responding differently to the same forcing. Understanding which picture is correct is essential for understanding how well Mars is protected from the solar wind. Question 3. How do the crustal magnetic fields affect atmospheric escape? As I mentioned earlier, Mars has patchy regions of magnetized crust, mostly in the southern hemisphere. These create mini magnetospheres that might protect the atmosphere beneath them, or might enhance escape by creating turbulent boundaries. Or they might do both depending on conditions. ESCAPADE will make measurements over both magnetized and unmagnetized regions, allowing direct comparisons. When the solar wind is calm, do the magnetized regions show less escape than unmagnetized regions? What about during solar storms? Do the crustal fields provide any protection, or do they make things worse? These questions are important not just for understanding Mars's history, but for evaluating proposals to use artificial magnetic fields to protect future Mars bases or even to terraform the planet. If natural crustal fields don't help, or if they actually make things worse, then artificial fields might not be the solution some people hope for. Question 4. How did atmospheric escape change over Mars's history? We can't go back in time, but we can study how escape rates depend on solar conditions. The sun was more active when it was young, with more frequent and more powerful solar flares and coronal mass ejections. By measuring how escape rates change during modern solar activity, scientists can extrapolate backward to understand what escape rates might have been like billions of years ago. ESCAPADE is launching during a period of increasing solar activity, as the sun approaches the maximum of its 11-year cycle. This is actually perfect timing for the mission. Solar maximum means more frequent solar storms, which means more opportunities to study how extreme conditions affect atmospheric escape. The data from these storm events will be crucial for understanding ancient escape rates. Question 5. What is the total rate of atmospheric escape from Mars today? This might seem like a question we should already know the answer to, but estimates from different methods have given different results. Some studies, based on measuring the isotopic composition of the Martian atmosphere, suggest that Mars has lost most of its atmosphere over its history. Other studies, based on measuring current escape rates, suggest the total loss has been more modest. ESCAPADE's comprehensive measurements will help resolve this discrepancy. By measuring escape from multiple locations simultaneously and over a range of conditions, the mission will provide the most accurate estimate yet of the total escape rate. This will help calibrate models that extrapolate backward through time. These are just some of the questions ESCAPADE will address. The mission will undoubtedly raise new questions as well. That's the nature of scientific exploration. Every mission to another world has discovered things that no one anticipated, and ESCAPADE will likely be no different. Let's zoom out even further and consider what ESCAPADE tells us about the future of planetary exploration. The space industry is undergoing a revolution right now, driven by commercial companies, new technologies, and changing philosophies about how to explore space. For most of the space age, planetary exploration was the exclusive domain of government space agencies. NASA, ESA, JAXA, and their counterparts built and operated all the missions to other planets. These missions were magnificent achievements of engineering and science, but they were also expensive and rare. A major planetary mission might fly once a decade. That's starting to change. Commercial companies are now building rockets that are dramatically cheaper than traditional launch vehicles. CubeSats and small satellites, originally developed for Earth orbit, are being adapted for deep space. Universities and small institutions that could never have afforded a traditional planetary mission are now designing spacecraft for other worlds. ESCAPADE is at the forefront of this revolution. It's a university-led mission using small spacecraft, launching on commercial rockets, and doing science that rivals what much larger missions have accomplished. If it succeeds, it will prove that this model works, opening the door to many more small planetary missions. We might imagine a future where dozens of small spacecraft explore the solar system simultaneously. Fleets of tiny probes could visit asteroids, map the moons of Jupiter and Saturn, study the atmosphere of Venus, and monitor conditions throughout the solar system. The two-spacecraft approach that ESCAPADE pioneered might become common, with constellation missions providing the kind of multi-point measurements that single spacecraft can never achieve. This doesn't mean large missions will go away. There will always be questions that require big, sophisticated spacecraft with heavy instrument payloads. But small missions can fill gaps in our knowledge, respond quickly to new discoveries, and do targeted science at a fraction of the cost. ESCAPADE also demonstrates the value of focused mission design. Rather than trying to do everything, the team identified specific questions and built spacecraft optimized to answer them. This focus allowed them to keep the mission small and affordable while still delivering breakthrough science. As we look toward the future of Mars exploration, ESCAPADE's findings will inform everything that comes next. Future missions to Mars will use ESCAPADE data to understand the radiation environment they'll encounter. Plans for human bases on Mars will incorporate knowledge about atmospheric escape and crustal magnetic fields. Proposals to terraform Mars or protect colonists with artificial magnetic fields will be evaluated based on what ESCAPADE reveals about how magnetic fields interact with the solar wind. The dream of humans walking on Mars is no longer science fiction. Multiple space agencies and commercial companies are actively working toward this goal. SpaceX has been developing Starship, a massive rocket designed to carry people to Mars. NASA has been developing technologies for Mars missions through programs like Artemis. China has announced ambitious plans for Mars exploration. When humans finally set foot on Mars, they'll owe a debt to missions like ESCAPADE. The little spacecraft that went before them will have revealed the invisible threats they face and pointed the way toward solutions. The science done by Blue and Gold will help keep those future explorers safe. But there's something even more fundamental at stake here. The question of why Mars lost its atmosphere is really a question about what makes a planet habitable. Earth and Mars started out similar, but they ended up very different. One became a cradle of life. The other became a frozen desert. Understanding why this happened is one of the deepest questions in planetary science. We now know that the answer involves magnetic fields, solar wind, atmospheric chemistry, and the internal evolution of planets. ESCAPADE will add crucial pieces to this puzzle. And as we discover more and more planets around other stars, thousands have been found already, with many more to come. This knowledge becomes increasingly important. When we look at an exoplanet orbiting a distant star, we want to know, could life exist there? Is there liquid water? Is there a thick enough atmosphere to sustain a climate? The answers depend on the same processes ESCAPADE is studying. Does the planet have a magnetic field? How does its star's wind affect its atmosphere? How have these factors changed over time? We can't send spacecraft to exoplanets. They're far too distant. But we can study the same processes in our own solar system and use that knowledge to interpret observations of distant worlds. Mars is a natural laboratory for understanding how planets lose their atmospheres, and ESCAPADE will make that laboratory more valuable than ever. The story of ESCAPADE is also a human story. Behind every space mission are thousands of people who dedicate years of their lives to making it happen. Engineers who design and build the spacecraft. Scientists who define the objectives and analyze the data. Managers who coordinate the complex web of activities. Technicians who assemble the hardware. Students who learn their craft by working on real missions. The ESCAPADE team includes veterans of previous Mars missions and newcomers getting their first taste of planetary exploration. It includes professors and students, contractors and civil servants, Americans and international partners. All of them share a common passion, the desire to explore, to understand, to push the boundaries of human knowledge. Space exploration has always been a cooperative endeavor. No single person, no single institution can do it alone. ESCAPADE represents this cooperation at its best. Universities working with NASA, scientists working with engineers, experienced veterans working with eager newcomers. This spirit of cooperation is as much a part of the mission as the spacecraft themselves. And let's not forget the public. Space missions are funded by taxpayers who believe that exploring the cosmos is worth the investment. Every image from Mars, every discovery about our solar system belongs to all of us. ESCAPADE will return data that scientists around the world will study for decades. It will answer questions that humans have wondered about for centuries. It will add to the sum of human knowledge in ways both large and small. As blue and gold make their way to Mars, millions of people will follow their journey. They'll watch the launch, celebrate the arrival, and marvel at the discoveries. This connection between space exploration and the public is vital. It reminds us that science is not just for scientists. It's for everyone who looks up at the sky and wonders. Now let me describe what the mission operations will look like once Blue and Gold reach Mars. Operating 2 spacecraft simultaneously around another planet is a complex undertaking that requires careful coordination. The Mission Operations Center will be the hub of activity. This is where controllers will send commands to the spacecraft and receive data in return. Because Mars is so far from Earth, ranging from about 55 million kilometers at closest approach to over 400 million kilometers when on the opposite side of the Sun, there's a significant time delay in communications. Signals take anywhere from 3 to 22 minutes to travel each way, depending on the relative positions of the planets. This time delay means that real-time control is impossible. Controllers can't drive the spacecraft like a remote control car. Instead, they must send sequences of commands that the spacecraft execute autonomously. These sequences are planned days in advance, carefully checking every detail to ensure nothing goes wrong. For ESCAPADE, the complexity is doubled because there are 2 spacecraft to manage. Each one needs its own sequences of commands. The orbits must be tracked precisely to ensure the spacecraft are where they need to be for scientific observations. Any anomalies or unexpected situations must be addressed for both spacecraft. The science operations are similarly complex. The goal is to get the most valuable scientific data given the constraints of power, communications bandwidth, and onboard memory. The team must decide which instruments to run, when, what data to prioritize for downlink, and how to coordinate observations between the 2 spacecraft. Some observations require careful coordination. For example, if scientists want to study how a disturbance propagates from one side of Mars to the other, they need both spacecraft to be taking measurements at the right times and places. This requires advanced planning based on orbital predictions and solar activity forecasts. Other observations are more opportunistic. If a coronal mass ejection is detected heading toward Mars, the team might change their plans to capture this event. These solar storms provide some of the most valuable data, but they can't be predicted far in advance. The team must be ready to respond quickly when the sun provides an opportunity. The data that comes back from Blue and Gold will be processed and archived for the entire scientific community to use. This is standard practice in NASA missions. The data is considered a public resource, not the property of the mission team alone. Scientists around the world will download ESCAPADE data and conduct their own analyses, looking for patterns and insights that the original team might have missed. This open data policy is one of the great strengths of modern space exploration. It multiplies the value of every mission by allowing countless researchers to participate. Some of the most important discoveries from space missions have come from scientists who had no connection to the original team, but saw something in the data that others had overlooked. Let's consider some of the technical challenges that the ESCAPADE team has had to overcome. Building spacecraft is hard. Building spacecraft that can survive the journey to another planet and operate reliably for years is even harder. One major challenge is thermal control. Spacecraft are exposed to extreme temperature variations. When facing the sun, surfaces can heat to well over 100 degrees Celsius. In shadow, temperatures can plummet to below -100 degrees. Electronic components and instruments need to stay within a much narrower temperature range to function properly. ESCAPADE spacecraft use a combination of insulation, heaters, and careful design to manage these temperature swings. The thermal engineers had to model every surface and component, predicting how heat would flow through the spacecraft under different conditions. They had to ensure that the batteries wouldn't get too cold, the electronics wouldn't get too hot, and the instruments would stay within their operating ranges. Another challenge is power. The spacecraft generate electricity using solar panels, which convert sunlight into electrical current. But the intensity of sunlight at Mars is only about 43% of what it is at Earth, because Mars is farther from the sun. This means the solar panels must be more efficient, larger, or both to generate enough power for the spacecraft's needs. ESCAPADE solar panels are sized to provide enough power even when Mars is at its farthest point from the sun, when sunlight is weakest. The team had to balance the need for power against the need to keep the spacecraft small and light. Every gram of solar panel is a gram that can't be used for something else. Communications is another critical system. The spacecraft must be able to send data back to Earth and receive commands from mission control. But the distances involved are vast, and the spacecraft are small with limited power for transmitting. The signals that reach Earth are incredibly faint, less than a billionth of a watt. To detect these faint signals, NASA uses the Deep Space Network, a global array of massive radio antennas located in California, Spain, and Australia. These antennas, some as large as 70 meters in diameter, can pick up whispers from the edge of the solar system. But even with these giant dishes, data rates from small spacecraft like ESCAPADE are limited. The team has had to prioritize carefully what data to send home. Navigation is yet another challenge. To get to Mars and enter the correct orbit, the team must know exactly where the spacecraft are and where they're going. This requires precise tracking using radio signals. By measuring the time it takes for signals to travel between Earth and the spacecraft, and the tiny shifts in frequency caused by their motion, navigators could determine positions and velocities with remarkable accuracy. But navigation at Mars is complicated by the planet itself. Mars is a lumpy gravity field due to uneven distribution of mass in its interior and crust. The spacecraft's orbits are perturbed by these gravity variations. The team must account for these effects in their navigation solutions, using models of Mars's gravity field developed from previous missions. The instruments themselves posed their own challenges. Scientific instruments are delicate devices that must be calibrated precisely to produce meaningful data. They must survive the violence of launch, the temperature extremes of space, and the radiation environment at Mars. They must operate reliably for years with no possibility of repair. The ESCAPADE instruments were tested extensively before launch. They were shaken on vibration tables to simulate the forces of launch. They were baked in thermal vacuum chambers to simulate the space environment. They were exposed to radiation to ensure they could handle the particles they'd encounter at Mars. Every possible failure mode was analyzed and addressed. Despite all this testing, there's always some risk that something will go wrong. Space is unforgiving of mistakes. A single component failure can doom a mission. The ESCAPADE team has done everything possible to minimize these risks. But they know that uncertainty is inherent in space exploration. This is why the two spacecraft design is so valuable. With two spacecraft, the mission has built-in redundancy. If one spacecraft experiences problems, the other can still return valuable science. This doesn't eliminate risk, but it does provide a margin of safety that single spacecraft missions lack. Let me talk about the broader context of Mars exploration. ESCAPADE doesn't exist in isolation. It's part of a decades-long effort to understand Mars, involving dozens of missions from multiple space agencies. The modern era of Mars exploration began in the 1960s with the first flyby missions. Mariner 4, launched by NASA in 1964, sent back the first close-up images of another planet. What those images showed was disappointing to many, a cratered, apparently dead world, more like the moon than like Earth. The dreams of Martian canals and civilizations were laid to rest. But as exploration continued, Mars revealed itself to be far more interesting than those first images suggested. Later missions discovered evidence of ancient water, dry river channels, minerals that form only in the presence of water, and layered deposits that suggested standing bodies of water. Mars had not always been the dry desert we see today. The question then became, what happened to the water? And the answer was intimately connected to what happened to the atmosphere. Without a thick atmosphere, liquid water cannot exist on the Martian surface. So understanding why Mars lost its atmosphere became a key question in understanding the planet's history. Missions like Mars Global Surveyor, Mars Odyssey, and Mars Express mapped the planet in unprecedented detail, revealing the remnant crustal magnetic fields and providing clues about the planet's geological history. The Mars exploration rovers, Spirit and Opportunity, found direct evidence that water had once flowed on the surface. The Curiosity rover discovered organic molecules and confirmed that Mars had once been habitable. Then came MAVEN, launched in 2013 specifically to study atmospheric escape. MAVEN confirmed that the solar wind is indeed stripping away the Martian atmosphere and made the first measurements of current escape rates. But MAVEN was a single spacecraft, limited in what it could reveal about the three-dimensional, time-varying process of atmospheric loss. ESCAPADE is the next step in this story. It builds on everything Maven learned while providing the multi-point measurements needed to go deeper. The science questions ESCAPADE will address couldn't even have been formulated without the groundwork laid by previous missions. And ESCAPADE won't be the end of the story. Future missions will build on what ESCAPADE discovers. Perhaps a mission to measure the crustal magnetic fields from low altitude, mapping them in more detail than ever before. Perhaps a mission to directly sample the escaping atmosphere, collecting particles and returning them to Earth for laboratory analysis. Perhaps a network of small satellites providing continuous monitoring of the Martian plasma environment. The pace of Mars exploration is accelerating. In addition to NASA's missions, other countries and commercial companies are increasingly active at Mars. China's Tianwen. One mission placed an orbiter and rover at Mars in 2021. The United Arab Emirates Hope orbiter is studying the Martian atmosphere. India's Mars orbiter mission demonstrated that countries' deep space capabilities. SpaceX has ambitions to send spacecraft and eventually people to Mars. All of these efforts contribute to our collective understanding of Mars. Data is shared internationally. Scientists collaborate across borders. The knowledge gained benefits all of humanity, regardless of which flag the spacecraft carries. ESCAPADE represents the collaborative spirit of modern space exploration. Although it's a NASA mission led by an American university, it involves international partners and will produce data that scientists worldwide will use. The questions it addresses about atmospheric escape, planetary habitability, and space weather are universal questions that affect how we understand planets throughout the universe. As blue and gold make their way to Mars, they carry with them the hopes and dreams of everyone who has ever looked at that reddish in the night sky and wondered what it was like. They're ambassadors of human curiosity, extensions of our senses into realms we cannot personally visit. When the first data comes back, it won't just be numbers on a screen. It will be answers to questions we've been asking for generations. Why did Mars become what it is today? Could life have existed there? What does Mars's fate tell us about the fate of other worlds, including our own? These are the questions that drive planetary science. They're questions about our place in the universe, about the conditions for life, about the future of our species. An ESCAPADE, two small spacecraft named after school colors, will help us answer them. The countdown to launch represents years of work by thousands of people. Every component was designed, tested, and installed with care. Every line of software was written and verified. Every procedure was practiced until it became second nature. And when those engines fire and blue and gold begin their journey to Mars, all of that work will be put to the test. Space exploration is a reminder of what humans can achieve when we work together toward a common goal. It's difficult, expensive, and risky, but the rewards in knowledge, inspiration, and capability are incalculable. ESCAPADE is one small part of this grand human endeavor, but it's an important part.